is actually a variational algorithm. So what I thought I will do is, instead of trying to cover a lot, I'll mostly walk through variational algorithms, and you will see that there are certain steps of variational algorithm. One of which is encoding, and this encoding varies from problem domain to problem domain. For chemistry problems, we have certain types of encoding. For machine learning problems, we will have some other types of encoding. And for combinatorial optimization problem, the encoding is encouraged, or the encoding directly comes from the structure of the problem, the structure of the graph, and solving that is what is QA/OA all about. So it is just the same variational algorithm, but the encoding is actually inspired from the graph theory or the graph problem that we are trying to solve underneath. Therefore, uh, if we understand if we understand the properties of variational algorithm very well, each and every property or each and every technique of variational algorithm that we will see will hold for QA/OA. During the variational algorithm discussion, I will not discuss too much on how to do the encoding. We will see that during when we go and talk about QA/OA. So that's at least my plan. Let's get started with this. If we ask ourselves, what are these algorithms about? If you see the first quantum algorithms that we study, the Deutsch-Jossa, Simons, all of these are some of the first quantum algorithms that we study when we start looking into quantum computing. These problems are what we call as purely quantum. Like, you start with something, say if we look into a Deutsch problem or a Deutsch-Jossa problem, you have some input lines and the entries of these are quantum. Let's just call it X. And then we have an oracle, which is also quantum. And finally, we measure, right? We measure, say, all the qubits or some of the qubits, depending on the problem. This is what the general quantum algorithms look like from the beginning that we have started looking into it. One of the major problems of these algorithms are that we directly write that, you need to feed in some input X, and then you have some oracle. Finally, you apply that oracle, and that oracle will do some say phase kickback type of things, and certain things will happen in between. You can do very nice mathematics with this, and finally you measure, and your outcome gives you the solution. In general, if you try, so it's a good practice. If you, I hope you have already done that, or the faculties who were doing that have already shown that. If not, I would definitely go and urge you to go and try out these early algorithms that you all have studied. Try this out in Qiskit. And in particular, what is important to notice, because this gives us a flavor of why we should look into some other forms of algorithms. This gives us a flavor. If we try to run this on Qiskit, we will see that this oracle needs to be prepared with many gates, right? And when we finally decompose it, it gets decomposed into a large number of gates. We see that the number of gates is very high, the depth of the circuit is very high. So all of these deep circuits, all of these actually prevents us from running these kind of algorithms in current quantum hardwares. Current quantum hardwares are noisy, and therefore we cannot really expect to run these kind of circuits which require a lot of gates, very deep circuits in the current devices. Which means that we we are which means that we are kind of restricted in some sense. What I mean by that is that we can learn all these algorithms, but we have to wait for the perfect machine to come, and we don't know when that will be, when we will have, say, millions of qubits, a lot and lot of um, physical qubits, which will create logical qubits, fault tolerance, error correction. All of those are there. We have to wait for all of those to happen, and only then we can run this algorithm. Naturally, the requirement was that we need to have something that we can run today, right now. We have the quantum devices available, so what can we run today? Natural answer was that, can we take an entire workflow? Say I want to solve some chemistry problems. I want to find out ground state of some molecule. There are already quantum phase estimation algorithms which we can use, but phase estimation algorithm will require a very sophisticated device. We need fault tolerance. So what can we do today? The answer that was proposed for that is that we can we can break down the entire workflow that we have, and we can have some part of that work going to the classical computer, some part of that going to the quantum computer. Leverage what is best for each. Like if I have an entire workflow and many steps going into that, not all steps will benefit from a quantum computer. So only take the step which will benefit from a quantum computer, feed it to a quantum computer. Otherwise, the rest of the parts of the workflow can go to a classical computer. What is the utility of this kind of workflow? The utility is that whenever you break down the entire workflow and make a very small part of it into quantum computer, the expectation is that the number of qubit requirements, the depth of the circuit of this small part will be very less, and therefore we can tackle it using the quantum computers that we have today. These kind of algorithms came to be known as this hybrid quantum classical algorithm, and the variational algorithm is actually one of the major family of this hybrid quantum classical algorithms. So what is this about? We will start by thinking that we have a Hamiltonian H, and we want to find out the ground state of something, because this Hamiltonian can come from physics, it can come from chemistry, it can come from optimization, it can come from finance, it can come from many different things. So for the beginning of this discussion today, let us not worry where the Hamiltonian is coming from. Let's say that the Hamiltonian is coming from some particular domain, and I don't care. For now, I will just treat it as a matrix. Let's take a simple matrix, say 3 0 0 minus 1. It's a diagonal matrix, just taking it for the sake of a good example. So what are the properties of this Hamiltonian? The first property is that it should be Hermitian. So what does Hermitian mean? It means that H is equal to H dagger, but it has a very important property that if it is a Hermitian matrix, then its eigenvalues are real. This is something which will be very handy for us, that the eigenvalues of these Hermitian operators are real. So therefore, when we take a Hamiltonian and we want to solve this time independent Schrodinger equation, which is essentially says that H psi is equal to, say, E psi. Here, H is my Hamiltonian. This is my Hamiltonian. E is my eigenvalue, and this psi is my eigenvector. So it's essentially an eigenvalue equation. Now the point is that if we find all the eigenvalues and the eigenvectors, so let's say that all the eigenvalues E0, E1, E2, say up to En. N eigenvalues are there, and I am interested in finding the minimum eigenvalue. This is what I am interested in, and a lot of things coming to say chemistry, the reaction rate often depends on the minimum eigenvalue. Similarly, stuffs like when phase transition occurs and certain stuffs like that in physics often depend on the minimum eigenvalue. So we can get some understanding of those properties by knowing the minimum eigenvalue, and the corresponding eigenstate, let's call it psi 0, is called the ground state. Okay, now the question here is, we all know how to solve this. I mean, we have all studied how to solve an eigenvalue equation. We are not going to repeat that. But the question is that why do we need some computation for this? Let's be very honest. Solving eigenvalue equation needs a lot of things, right? We need to put this h minus lambda I equal to 0 and all sort of things, and then we will have a set of linear equations that we have to solve. Now the point is that if I take a Hamiltonian, if I take an n qubit system, the corresponding Hamiltonian is of the order 2 to the power n cross 2 to the power n. So it's a huge matrix, which means it has 2 to the power n eigenvalues. How can we find out which one is the minimum eigenvalue? We can find it out by just calculating all the eigenvalues and then finding the minimum one of that. This is of course difficult, and it is very difficult to scale, as we can understand, because of this exponential growth in the size of the Hamiltonian and hence the number of eigenvalues. Therefore, currently, if we use computational methods, there are classical computational methods in NumPy. If you go to NumPy, there is this linear algebra package, and there is this I function from there, same in MATLAB or wherever you want to try, which will give you the eigenvalue and eigenvectors given a matrix. But of course, that is for a small n. We cannot really say if I want to know this for 50 qubits, not possible. Even if I want to know this, maybe 50 qubits, not possible. What do we do then? So the example that came out with this idea of variational algorithm is, if I don't know the answer, let's guess the answer. How do we guess it? We start with some trial wave function. For now, let's only have the mathematical part, and we will just immediately see some more concrete examples of this. So I have some trial wave function, and this theta is a vector. So it means that this wave function is represented by, say, some k parameters. So you can think of this as some psi theta 1, theta 2. There are k unknown thetas. And if you can put the values of the thetas properly, then you know the minimum eigenvalue. You obtain the ground state, you know the minimum eigenvalue and everything. Now the question is that how do you know? How do you know the good values of theta? Well, of course, we don't know to start with. Therefore, we will start with some random guess. So we can start with some random guess. Because we don't know some good values, what we will do then is say in iteration I have the state psi of, say, theta I. This is a vector once more. This theta is a vector. That means there are k of such values. I'm just calling in iteration I am just calling this as theta I. Now, how do I know how good or how bad this is? For that, I need to calculate expectation value. I don't know how many of you were there in the last module. We spend a substantial amount of time talking about how to calculate expectation values. So I'll not go into that much detail today. Otherwise, like we will end up spending a lot of time there itself. The expectation value will be calculated like this. Next, what we do is we update the theta, select new set of parameters, theta I plus 1, and we start iteration I plus 1. So we from here we just go back to here from the second step. Now, if we look into this entire, so this algorithm is very simple, right? That you guess, and every time you try to refine your guess. And hopefully, if you keep doing that, we will start going towards a very good solution. So just yeah. So if you look into this algorithm, we will immediately realize that all the steps here doesn't need a quantum computer. So when we say we start with random guess, this is classical. It's just creating k random numbers. So this is just classical. We don't need a quantum random number generator or anything for that. Now I need to create this state, this psi of theta I. This is of course quantum. This is of course quantum. How do I calculate the expectation values? I measure and then classically do a post processing. So this is measure plus classical post processing. Measure, we measure in the quantum computer and we classical post processing. So that means when we measure, we get some bit strings, zeros and ones. And then we have to just do a weighted sum over this. So this weighted sum can be done in classical. So this I already wrote classical post processing. So this is classical. There is nothing quantum about this. And finally, when we say that you select a new set of parameters theta I plus 1, this is also classical, and a lot of very well developed algorithms exist on how do you minimize. I mean, you can even think of this as a gradient descent algorithm. Whether gradient descent is the best algorithm for this or not, we will try to see if we can have time to argue about these things. But this can even just be a gradient descent algorithm. I am just trying to find a new set of parameters. So it's essentially classical. So you see what it means by saying that it's a hybrid quantum classical algorithm, because this entire workflow, part of it happens in a quantum system, part of it happens in a classical system. So what we hope is that the corresponding quantum circuit, that is this one, will be much shallow, which will contain fewer gates, and therefore will be way more easier to create on a quantum circuit and to run on near-term quantum circuits. Okay. The first question from that should come from here is that you are trying to calculate this expectation value, and this expectation value gives you the energy E. And every time when I'm trying to find a new set of parameters, what I mean is that I am expecting that when I go to iteration I plus 1 with this new set of parameters, it will give me a lower energy. And I will keep getting lower and lower energy until I reach the absolute lowest energy or very close to it. Some convergence criteria will be there. The first question that we should consider here is, how do we guarantee that I won't get a false positive answer? What this means is, let's say you keep on running this again and again, and your final answer, final expectation value, uh, final answer is say EF. How do we know that EF is always greater than or equal to E0? It is never less than E0. So what is the guarantee of having this? Because since I am just tuning some parameters and I'm trying to find some good wave functions, and I'm just trying to find good parameters which will create good wave functions. Therefore, it is possible that I end up with some value of uh, parameters such that my final result is actually less than the lowest eigenvalue. So I am telling you an incorrect answer. And this can be very bad in many real world problems. So what we can show here is, let's say that I have the eigenvectors psi1, psi2 up to some psi n. Okay, these are my eigenvectors. Now, if you see the Schrodinger equation, what it says is equal to EI psi I. This is the definition of eigenvectors. This is what the eigenvalue equation is. So now, if I look into what this means, psi I, H psi I, this is essentially psi I, EI psi I, and EI is just a number. So it is EI psi I, and we know that psi I is normalized. It's a quantum state. So that's EI. That's what we just saw before, that the expectation value gives me the energy. Now I can always write it that this is EI is greater than equal to, so EI should be greater than or equal to E0, correct? For any EI, it should be greater than equal to E0, and this comes from the eigenvalue equation. We cannot have a scenario where EI becomes less than E0. And this is the variational principle. It's as simple as this. Sorry. Okay. So it is as simple as this. This is called the variational principle. Variational principle. And the name variational algorithm comes from here. This is, sorry. So this is called the variational principle, that as you keep varying your state, as you keep varying your state in any way, whatever energy that you get out of this, which is the expectation value, it can never go below the best solution. Therefore, the variational algorithms work. In some sense, the variational algorithm works. How do you find out good theta I? All of these questions are there. But assuming that we can do all of these, this approach cannot give me a wrong solution. So that is great. Sorry. What I mean is that this approach can give me a wrong solution. It cannot give me a false positive answer, which means it cannot give me an answer which is lower than the lowest eigenvalue of the actual system. Whatever I am going to get is at least greater than or equal to. Ideally, I want to find out good parameters so that my final estimate EF is equal to E0. That's my final goal. but I can have some other convergence criteria as well. Say I will try this only 100 times or something. These are the things we just do in classical machine learning as well. That instead of trying to find the best solution, maybe I can say I'll do this iteration 100 times, 1,000 times, or I will stop if my energy E is not getting lowered significantly on every step. So these are some early stopping criteria that we can have. But whatever we do, we are guaranteed to get something which is at least greater than or equal to E0. It can be off, but it can be off in this upper bound kind of thing. Okay, great. So the question now is, how do we create this psi theta, right? And as I said that initially we will talk about general variational algorithms. So I will not right now show you some very sophisticated way to create that. But let's take this example Hamiltonian. My example Hamiltonian here was, we will see a much more sophisticated way of creating that when we go to QAOA. And I have purposefully taken this as a diagonal Hamiltonian, which means my say eigenvalues. If I say eigenvalues and eigenvectors, my eigenvalue can be 3, and the corresponding eigenvector will be 1, 0, which is the state 0, or -1, the corresponding eigenvector will be 0, 1, which is 1. So if I want to find out my minimum eigenvalue state, which will be my ground state, for this Hamiltonian, this is my minimum eigenvalue state, therefore this is my ground state. Okay. um, Make sure that you don't get confused here that, oh, one, usually we say one is higher. um, we say one is the excited state, 0 is the ground state. We do, but given the Hamiltonian that I have taken for this problem, it has two eigenvalues, and the lower eigenvalue corresponding to the state 1. Therefore this is the ground state energy, -1 is the ground state energy, and 1 is my ground state. Okay. Now the question is that how do we find it? How do I create my circuit? The first thing that we can do here, once more, at this point, this won't be a very sophisticated way of tackling this. Let's say that I have a circuit which is just some R Y theta, a single gate. It is anyway a 1-qubit system, so I just have a single gate and I will measure. Done. Now, if I see how Ry works on the state 0, it gives cos theta 0 plus sine theta 1, right? So now we can think of many iterations ongoing. Let's say that my iterations, iteration 1, value of theta, and this is my exp val, which is the expectation value. Let's say on the first iteration, I start with 0. I could have started with something else, but 0 is as good at random guess as anything, right? So if we start with 0, we see that our corresponding state, maybe I would want to write my state here and then the exp val. So my corresponding state here, cos 0 is 1, sine 0 is 0. So that means my corresponding state is 0. And then my exp val is essentially 3. Okay, how do I know that? I hope you all remember this interesting spectral decomposition. Let me just take a moment to uh, recapitulate this. If I give you a Hamiltonian H, how many unknowns do you need to know? So you can always write down a Hamiltonian H, which is a Hermitian operator, which means it is also a density matrix. So if you are able to make these connections, awesome. If not, don't worry about this. But also a property of a density matrix is that it should be positive semi-definite. It's a Hermitian operator. So for now, let's stick to a Hermitian matrix. I can always write down my Hermitian matrix, say as 0, 0. I'm just taking a single qubit. 0, 1 plus A1, 0 plus 1, 1. Right? So this 0, 0, if I write down the matrix here, this is my 0, 0. This is my 0, 1. This is my 1, 0. This is my 1, 1. So there are 4 entries. I need to know these A00, A01, A10, A11, these 4 values. If I know these 4 values, then I am done. But if I can diagonalize this matrix, that means if I can know the eigenvalues and eigenvectors of this matrix, then essentially I can write it down as 0, 0, 1, 1. These will be my eigen values. It will be a diagonal matrix. These are my eigenvalues, and these eigenvalues here are 0. That means if I just know A00 plus A11, I am assuming it is diagonal in this basis, then I am done. Correct? So this is basically called a spectral decomposition, that you can just write a matrix, a Hermitian matrix like this. This is the spectral decomposition of a matrix. So just by doing spectral decomposition, we can see that this will be, so you can take this as 0, H acting on 0, H acting on 0 gives me 3, so this is 3. Now let's say in iteration 2, I update this to pi by 4. If I update this to pi by 4, then cos pi by 4 is 1 over root 2. So this state becomes 1 over root 2, 0 plus 1, which is the plus state. And so this is basically the plus state. So if I apply, not 0, sorry. Now it is the plus state. So if I apply this, it will be something. We will have to calculate. It will be something. Anybody wants to calculate this? So if you just calculate this, what will this be? Let's see. This will just be 1 over root 2, 1 over root 2. So half is out. And then I have this 0, 3, 0 plus 0 minus 1, 1 plus 1, 3, 0 plus 1 minus 1, 1. If this calculation is not immediately clear, I would request you all to please go ahead and try this out yourself. This should be a fairly easy calculation. So I get a 3 from here. This part, the second and the third terms are orthogonal to each other, so they cancel each other out, and I get a minus 1 from here. So I get, so what I obtain is 3 minus 1 is 2 divided by 2, which is 1. What this tells me is the choice of theta as pi by 4 is actually a better choice. So my quantum circuit of Ry pi by 4 is actually a better quantum circuit than if I put theta equal to 0. So instead of stretching this a lot, if I just take, say, pi by 2 here, then cos pi by 2 is 0, sin pi by 2 is 1. This state becomes 1. and the exp val immediately becomes -1, and we have obtained the final solution. So this is how a variational algorithm works. Of course, for more complicated problems, we will have a much more complicated circuit. The number of iterations that happened here will be a lot more iterations, but the essence of the algorithm is what we just discussed. Nothing more than this, right? Maybe we can stop for a minute and see if anybody has questions. I don't see any questions in chat, but if you have any questions, like, we can stop maybe and take. Okay, if not, we can continue for now, and we will take questions as we go ahead. This is how a variational algorithm is going to work, right? What we just saw. So now let's try to think of a few cases. First, see what are we trading off and what are we gaining. This circuit is shallow, which means that this circuit is way better to run on the near term quantum devices than all those phase estimation or those kind of algorithms, which can also like calculate the eigenvalues and eigenvectors for these things. This is point one. But what are we trading this for? I am getting a shallow circuit, but now I need to run my circuit many, many times. I have shown 3 iterations here, and you can understand that for more complicated problems, we can have many, many more iterations, of course. So we are trading off the number of executions for the depth of the circuit. This is what my variational algorithm is doing for me. Okay, so I see there are a few questions here. Um, how do we get 3 unexpected values? Okay, so if you look into this, if you look into this particular H, the H that I have taken, I hope that should also answer the other question on how do I get plus H plus. It's 300 minus 1. So this is essentially 3 times 00 plus minus 1 times 1 1. And as I said, this point of the matrix is 0 0, this is 0 1, this is 1 0, this is 1 1, and so this is 0 0, this is 0 1, this is 1 0, this is 1 1, and therefore I can write it like this is 3 times 0 0, because the coefficient at this point here is 3. There is the coefficient of 0 1 and 1 0 is 0, and the coefficient of 1 1 is minus 1. So I can say that my matrix looks like this. So now if I take this part, what does this mean? It essentially means that you are applying your H on 0, correct? This means we take this part, it is that apply your H on 0. And we have this eigenvalue equation. So here what we talked about, the eigenvalue of this is 3 and the eigenvector is 0. So that means H acting on 0 is 3 times 0. This is just the eigenvalue equation. And H acting on 1 is minus 1 times 1. This is coming from this eigenvalues and eigenvectors. So we can take that, we can check this in 2 ways. We can take that and say H acting on 0 is just 3 times 0. Now 3 is just a number, so we can take this 3 out, and I get an inner product between 0 and 0, which is always 1 because the states are normalized. So that gives me 3. The other way we can calculate the same thing is if we just write down this matrix. I mean, this one is easier essentially. Now, if we break it, it is just, sorry, now if we break it, it is just 0, 3, 0, 0, 0 plus minus 1, 1, 1, 0. Now this is 1, this is 0, and therefore I am left with 0, 3, 0. This part gets cancelled out, the second part, because this is 0. So it is basically 3 times, sorry, 0, 0, which is 3. Similarly, you can calculate this plus h plus. Just break plus into 1 over root 2 0 plus 1 over root 2 1. Right? Yes, I'm coming to practical examples with QAOA. Like QAOA will be a direct practical example of this. For now, let's, for the time being, stick to this kind of toy Hamiltonian, which is just mathematical abstraction. So first, we understand that we can create an ansatz. This is called an ansatz. This circuit, ansatz. This circuit is called an ansatz, which is kind of a guess. Ansatz, essentially, it will mean a guess. I am guessing some values of theta, and I am trying to refine myself on every step to reach the absolute or the proper solution that we can have, best solution that we can have. That is the quantum part of it. Now coming to this, how do you go from 0 to pi by 4, from pi by 4 to pi by 2? These I just selected randomly here. How do you do these things? There are essentially many classical algorithms that can do that. You can select any one of them. There are many classical algorithms. Often you will see a very famous algorithm which gets used is something called Kobila. I'll just tell the working principle behind Kobila. The working principle is very simple, that you just try to uh, slightly vary a parameter. So let's say that you have these parameters theta 1, theta 2, up to theta k. This is your, say, first iteration. In the next iteration, you just vary theta 1 by theta 1 plus delta theta 1. Small perturbation here. And now you check whether exp val increased or decreased. Similarly, so if it increases, you know that I should be increasing theta 1. If it decreases, you know, okay, say we are trying to minimize the expectation value here. So if it decreases, you know that, okay, theta 1 should increase. If it increases, you know that, no, theta 1, whatever I did with the previous value was good. Maybe I can decrease it, I should not increase it. Similarly, in the next step, you keep theta 1 unchanged, you do change theta 2 a bit. And you check the same thing again. You do this for each of the k parameters. So do repeat for all k. What this is telling me is whether I should increase theta 1 or not, whether I should increase theta 2 or not, and so on. This you know for every parameter. Next, what I will do is I will vary theta 1 and theta 2 together. So I will say, so let's say that what I understood from here, let's assume that if I increase theta 1, expectation value is going down. If I decrease theta, if I increase theta 2, expectation value is going up. So I know that I should be increasing theta 1, I should not increase theta 2. This is what I have understood from here. So in after understanding each of these for each of the individual parameters, I start with linear combination of these. So I will increase theta 1 because increasing theta 1 was better. I will decrease theta 2 because increasing theta 2 was worse. So I'll decrease theta 2. And like this, I will try these various combinations. So like this, try various combinations. So what you can feel immediately. Okay, so there are some questions on expectation values. I would request you to please look into the videos from the previous QT that I did. I know the organizers can give you that video. We kind of spent an hour there discussing about expectation values. I really don't want to go into 1 hour of expectation value discussion here again. Otherwise, we will just miss out all the parts that we are supposed to cover today. Um, Okay, let's come to this. So initially, it may feel that this is not a very sophisticated algorithm, right? Because you are just randomly trying some variables, increase, decrease, then you are trying their linear combination. There are so many possible combinations to try out. I would agree that okay, this is not a very sophisticated algorithm, but again, I will tell you that one of the most common algorithms that you will see here, you will see used in the variational algorithms is Cobila. Why so? Because what you can understand that in order to get a new set of parameters, you don't need any hardware experiment. So to go from theta this to this, you don't need an hardware experiment. What you need here, when you calculate whether expectation value has increased or decreased, you need to run your circuit. So if there are I iterations, then you need to run the circuit on the quantum computer I times. Nothing more than that. That's all. So running on quantum computers is costly. Therefore, this is actually something which is very much preferred by many researchers because it just reduces the number of computation runs that you need on a quantum computer. Every time you have a new set of parameter, you run it on a quantum computer and see whether the value is better or not. But when when you update your parameter, there is a very fixed rule on how to update that, and that doesn't depend on your you don't have to run anything on quantum computer to decide that I will go from this theta 1 theta 2 theta 3 to theta 1 plus delta theta 1 this value. You don't need a quantum computer for that. But as perhaps you all are thinking at this point, but that this algorithm doesn't seem very sophisticated. You are just, I mean, this is just kind of trial and error. I would agree. There are many. This is called a gradient-free algorithm. This is called a gradient-free algorithm. Why we will see understand immediately. One of the very famous algorithms that we have is of course gradient descent. So what it will do, it will try to change each one of these parameters. So I will vary each one of this, each one of the parameters and calculate gradient. So let's remember, how do we calculate gradient? If I want to go for some differential of h, it is essentially some limit, say delta h tends to 0, f of h plus delta h plus f of h minus delta h by 2. So this is how we calculate the differential, and this is how we get the gradient. Now what this is telling me, when I vary each one of the parameter and calculate the gradient, it gives me a very good information that it tells me which direction, and when I say direction, I mean along these parameters, which direction has the highest gradient. So I will follow that path. Whichever is maximizing my whichever is giving me the maximal reduction in the expectation value, whichever parameter change, that is the parameter or that is the path that I will follow henceforth. So let's say that from here I found that theta 1 or say theta 2 is giving me the highest gradient. So I will make sure that for every run henceforth, I have changed theta 2 to theta 2 minus delta theta 2. So let's say, sorry about that. So let's assume, say theta 2 as the largest gradient. So when I try my next iteration, I will always make sure that I have, instead of theta 2, I have theta 2 minus delta theta 2. And then I will again calculate gradient and so on. But what changed from here, here I changed theta 1 first, then I changed theta 2 first, then I changed theta 3. I was changing each one of them. But here, since I know that theta 2 has given me the largest gradient, I will make sure that every time theta 2 is theta 2 minus delta theta 2. Next time I won't change theta 2 minus delta theta 2 back to theta 2. That will not happen ever. So it is very similar to the kind of gradient descent algorithms that we do in um, these simulated annealing or machine learning, all of these kind of things. So this is very nice because we know how good it can be from our classical understanding also. What are the drawbacks here of this method? The first drawback, it can get stuck in local minima. We know that gradient descent is very good if we have a convex structure. But of course, most of the time, the cost function will not have a very nice convex structure. The landscape of the cost function can be very, very complicated, and therefore it can get stuck in local minima. Another major drawback of this, how do you vary each one of the parameter and calculate gradient? We said this is how we calculate gradient. So to calculate this f of theta plus delta theta, I need a quantum circuit. So to calculate, say, h plus delta h or theta plus delta theta, we need a quantum circuit which will start from 0. This will be rh ry theta plus delta theta, and to calculate f of theta minus h minus delta h, say that is theta minus delta theta, we need another circuit which will be of this form. Therefore, to calculate gradient of each parameter, I need two quantum circuits. Two quantum circuits to calculate gradient for each parameter. This can become very costly, right? This can become very, very costly because say you have 50 parameters. Therefore, to in each iteration, you need 100 circuit executions. And then you don't know how many. So when I say one iteration, there are 50 parameters. To calculate the gradient of each parameter, you need two quantum circuits. Therefore, just to go from this first iteration I to iteration I plus 1, you need 100 circuit executions. And let's say um, you are having 100 such iterations. So it is 100 times 100 circuit executions, which is a lot, which is no doubt a lot. But at the same time, I specifically mentioned the drawbacks, but there is a huge advantage that unlike Kobila, which is kind of just doing some trial and error kind of way to find the best direction to go towards, gradient descent is using the gradient of the cost function to actually drive the algorithm towards the minima. So it has some good advantage, but it comes with its own disadvantage that you have to run many quantum circuits for this. One of the very highly used algorithm for this, again, don't quote me or anything that, oh, he has said this is the best algorithm. It is very difficult to say that this is the best algorithm, but this kind of takes the best of both if you think in some way. The main drawback here was that it can get stuck in local minima versus you kind of get this two quantum circuits for each parameter. On the other hand, the advantage was that it actually drives the algorithm towards the through the gradient towards the minima. So what SPSA does is that if you have theta 1, theta 2, theta 3, theta k, in the next iteration, it applies a random perturbation on each one of them. So apply random perturbation on each. And if you consider this perturbation to be, say, some a, then we can get something like theta 1 plus a times theta 1. A is very small, let's assume. You can even take that a within some range. Say it can be positive, it can be negative. It's a random number, right? So a is not fixed. A is random for each parameter. It is not fixed. Then you can think, or let's call this a1 just to be, say, theta 2 plus a2 theta 2 and so on. Now what it means is that here what I am just doing is I am just telling you that you need to calculate the gradient in such a way that you have a perturbation for each one of them at the same time. So what you can do is you can just do away with two quantum circuits in each iteration. Just to you want to calculate the gradient of this new set of parameters, right? You want to calculate gradient. We know that to calculate gradient, I need two quantum circuits for each parameter, because here I am calculating gradient with respect to theta 1 first. Then I am calculating gradient with respect to theta 2, then with respect to theta 3, and so on. Here I am calculating gradient with respect to this entire thing, which means only two quantum circuits required. Circuits required for each iteration, irrespective of the number of parameters that you have. This is a huge save. Irrespective of the number of parameters you have, just like before I was saying in gradient descent, if you have 50 parameters, you need to run 100 quantum circuits in each iteration. Here you can only run two quantum circuits each iteration, irrespective of how many parameters you have. And since you are using gradient, it still retains the benefit of gradient descent. That means it is driving the system towards, what you understand is that this random perturbation that you are creating, whether that is giving you a higher gradient or not. If it is not, you discard, you try with some other random perturbation. So you are still driving your system down towards the gradient. So the algorithm is still algorithm driven by the gradient. And the third thing is that since you are applying a random perturbation, it has a tendency to be able to overcome local minima. Because of random perturbation, it can often overcome local minima. So, in some sense, again, I would say don't go and quote me there, because people from mathematics and optimization, they can get very angry on this. But in terms of practice, as you see, SPSA kind of has the best of both. It requires very few quantum circuits in each iteration. Why is Kobila so widely used? Because it does not use any quantum circuit for any gradient calculation. Each iteration, you only need one quantum circuit execution. Here, each iteration in SPSA, you need two quantum circuit execution. So the increase in the overhead is not huge, unlike gradient descent where you would need two times the number of parameters, which can be huge. And at the same time, it is still using the gradient information. That means it is not like a blind guess like what Kobila is trying to do. It is trying to blindly guess which way to go. It is not doing that. It is kind of trying to figure out the gradient and therefore drive its algorithm towards that. And at the same time, applying these random perturbations often helps it to overcome local minima, making SPSA one of the most widely used classical algorithms for these kind of variational problems. Having said that, keep in mind a few things, that these classical algorithms, these are things you know, like when I'm talking of classical algorithms, these are just classical. So everything that you have studied in classical systems, they hold here. These classical algorithms have a set of hyperparameters. What are the hyperparameters? This say the random perturbation. Say this random perturbation A that I was talking about. What is a good value of A? Big question. What is a good value of A? Second, learning rate. We know that in gradient descent that this all this learning rate, that you want to start with a high learning rate, and as you go, as you keep going, you want to reduce the learning rate so that you don't miss out the exact optima. All of these things, these are great. But if I ask you that, okay, I understand that I need to start with a large value of eta, the learning rate, and I would slowly reduce the value of eta so that I don't cross across the global minima. All of these are good, but tell me, what do you mean by large? Tell me, what do you mean by small? How much should I reduce? There are no obvious answers to these. So these things are called hyperparameters. Just keep in mind that when I say parameters, these theta 1, theta 2, these are parameters. These values, which I am inherently kind of telling you, just change by this. You just change this much. So what is this much? That is called a hyperparameter. And sorry, why, I don't know why this is happening. Anyway, so these are called the hyperparameters. Selection of hyperparameter is not trivial. Selection of hyperparameter is often non-trivial, and the performance of your algorithm depends largely on how good you are able to select your hyperparameters. And performance depends on the choice of hyperparameters. Right. So that is kind of an overview of how these algorithms work. I hope this was more or less clear. We can once more stop and see if there are some questions, and we will accordingly progress from this. So if you have questions, let's take some now, and then we can again go ahead. Okay, so the question, one question that is here is, what is random perturbation? Random perturbation basically means that you are taking this theta 1, and let's say previously what I was doing, previously here I was saying that you change theta 1 to theta 1 plus delta theta 1. Next time you change theta 2 to theta 2 plus delta theta 2. So here what you can do is you can choose an A, or you can just say it is plus 1 minus 1. Randomly choose a list of plus 1 or minus 1 k for each parameter, for each parameter. Change the parameter accordingly. Let's say you have a you have 5 parameters, and you select this random list L as, say, plus 1 plus 1 minus 1 plus 1 minus 1. Okay, 5. Then your new params will be this theta 1 plus delta theta 1, theta 2 plus delta theta 2, theta 3 minus delta theta 3, theta 4 plus delta theta 4, theta 5 minus delta theta 5. All of them at the same time. How much is delta theta? That depends on your learning rate. Once more, that's hyperparameter, and finding good hyperparameter is difficult. There is no trivial answer to that. What is your delta theta? No trivial answer to that. But this is how we just directly change all the parameters at the same time in each iteration. So that's what I mean by this random perturbation. Okay, good. So let's go ahead if there are no more questions at this point. So we understand first, not very, not in much detail, but we understand how we create an ansatz. For now we have just randomly created the ansatz. We understand the variational parameter, or in overall sense how the variational algorithm works. That's the variational thing, parameter, the variational principle. We understand how to create the ansatz. We understand how to change the parameters theta. We understand some of the classical algorithms which are there in some, not too much detail, and we understand some um, pros and cons of each of these algorithms. One of the major issues that we get, so I mean, let's give some not so nice words from at this point. What do you think is the bottleneck of this algorithm? See, if you say how to create the answers, no, we haven't studied in detail yet how to create the answers, but there are very sophisticated ways, and we will immediately now go to QAOA. Just after this discussion, we'll go to QAOA and we'll see how to create an ansatz properly from a given problem. So creating an ansatz is not a problem. Calculating expectation value, definitely not a problem. Selecting new set of parameters, we have already seen different algorithms. We have seen the pros and cons of each of those algorithms. Select whichever one you like. All these steps are very well defined. What is not well defined is how many times this iteration will go. This is not well defined. This is a major bottleneck of these kind of algorithms, that these algorithms can go on many times before convergence. Of course you can make an early stop, but that early stop doesn't guarantee you a very good result. And therefore one of the major belief among many of the quantum researchers at this point is that this kind of variational algorithms are very good for toy problems, toy Hamiltonian, small use cases, small graphs, small molecule, all of those. But if you are really trying to push the limit of quantum computing, if you are really trying to go into if you are really trying to go into a domain where classical algorithms are struggling, you cannot do that using this method. It's just the number of times this iterations goes makes things pretty bad. And I can give you one example, something that used to be on the IBM quantum learning platform, which will perhaps most likely be changed, is that for a 2 qubit system, with I think 10 parameters or something, it takes around 73 minutes to converge. Now, mind that this is huge. A 2 qubit system means a 4 cross 4 Hamiltonian. You could directly just solve that by hand, or you can just use MATLAB, NumPy, whatever you want. It won't even take a second for you to solve it. It's a 4 cross 4 matrix. So using 73 minutes on a quantum computer for this makes no sense. Therefore, a very major belief in the community at this point is that this kind of algorithm is not going to give us advantage. There are some better versions of these algorithms, some more advanced versions of variational algorithms, I would say, which are called this quantum centric supercomputing algorithms, which are way more suited for towards quantum advantage than these kind of variational algorithms. But at the same time, it is important to understand these variational algorithms to realize the drawbacks. And there are some very good science behind this. So it's important to take these things before we move on to other parts or more advanced things like this quantum centric supercomputing that I was talking about. So don't feel that, okay, oh, he's already saying that this is of no good, so why are we just wasting our time today? No, this is actually important to understand how it is going. It uses some very interesting science, and as I told you, even the quantum centric supercomputing is a form of a variational algorithm, not exactly like this, in a slightly different way. And therefore it is important to understand the concepts that come from here, but at the same time also realize the limitations of these kind of algorithms. Okay, there is one question to give a summarized view or glance of variational algorithms. I think like this is the most summarized view I can think of, that you create an ansatz in some way, you create a trial wave function or an ansatz with some parameters. We start with some random guess, and in each iteration, we create a quantum circuit with some values of these parameters. We measure and calculate the expectation value, and then in the next iteration I try to come up with a new or a better set of parameters using the algorithms, some of the algorithms that we discussed, so that we can go and if we keep repeating this, we will get better and better solution. That is the expectation. Eventually we will converge, hopefully, to the optimal solution or very close to the optimal solution. One of the major limitations of variational algorithms is something called a barren plateau. I hope I wrote the spelling right. It's plateau. The idea of this is that, say, when I'm doing this gradient based approaches, um, even if I am not doing gradient based approach, what you see here in Kubila also, it is in some way in a very crude manner trying to understand the gradient but not properly using the gradient information. Now, what is often seen is we won't really have time. We are almost close to 6, so I still need to go to QAOA. What we are already seeing here is, if you start increasing the size of the system, point one, if you increase number of qubits or gates, this is one reason. The second point is noise in the system. Both of these result in something called the flattening of the cost function landscape. In other words, you would really want a landscape which is, say, this is a very good landscape in some sense. Of course, there are many local minima, but I would still say it is a good landscape because it is very sharp. So you can easily calculate the gradient. But when we have noise, or as the size of the system starts growing, the system starts getting like this. So you see many plateau regions here. You see many plateau. This is a bad landscape. Why is this a bad landscape? You can understand immediately that if you are sitting here and you are trying to identify the gradient, well, every direction it will show you that, oh, you are already in the, everywhere is flat. So there is no gradient in any direction. What essentially happens when I say this, that the gradient actually reduces exponentially with the strength of the noise or the size of the circuit. So the gradient starts decreasing means the landscape starts getting flatter and flatter. That means you don't get any gradient and you don't know which direction to move to. So it's a very bad landscape, and this barren plateau is a major problem of of this variational algorithms. And there are many researches which try to deal with barren plateaus. There have been many different techniques where people are trying to come up with how to deal with barren plateau. I mean, some of these techniques are of one very interesting technique is called CVAR, conditional variance at risk. What it says is that when we are calculating the expectation value here, there can be some, there is noise, right? So some of the outputs can be pretty good, some of the outputs can be pretty bad because they are affected by noise. So we will see, we will calculate the expectation value individually for each one of them. We'll calculate the energy for each of the outcome, and then we will take only the best few of them to decide what the next iteration will be. So instead of taking an average over everything, I take only, say, the first one third. That is the best one third outcome. This is one method to do. There are other techniques where they say that, okay, instead of fixing your ansatz, it is always going to be an RY gate. Instead of fixing your ansatz like this, you have a pool of ansatz. So you have a pool of operators. And now you, at every iteration, instead of saying I will always apply my RY gate, let's take the pool of operators, start putting in every gate from the pool, and we build the circuit like that. We select that operator which maximizes my gradient, or yeah, which maximizes my gives me the largest gradient. So whichever operator is helping me prune this bad landscape, or whichever operator is helping me avoid this bad landscape, I will use that operator. So this is again a very good approach, and it is often shown to, because even if you see there is no, even if you forget about the barren plateau, the noise in the system, you are, instead of fixing your ansatz that this is always going to be this particular gate, you are selecting a gate in each iteration from a pool of operators, and you are keeping that gate which gives you the highest gradient. So this method is often shown to actually converge much faster than the uh, trivial or the vanilla method that we discussed today. But you understand that if you have a pool of say 10 operators, you have to calculate the gradient for all 10 of them. So the number of circuit executions that you need increases with the size of the pool of operator that you have. There is something called this warm start. What warm start means is that, why are we solving this using a quantum classical hybrid algorithm? Usually because this Hamiltonian is too big and I cannot solve that using a classical method. But instead of randomly starting with some random guess, and say your random guess is here in this point, in this barren plateau, say your random guess is in a very bad location, this can happen, right? And then you are stuck in a very beginning and you cannot improve upon your result. So warm start is one of the examples where you try to solve this approximately using a classical computer. You cannot directly solve it on a classical computer for big problems. If you can directly solve it on a classical computer, why even go to a quantum computer for that? So you approximately try to solve the problem, start with some approximate solution, and instead of a random guess, start with that good enough solution. Not the best solution, but some better solution than the random guess. So this is called a warm start kind of method. People have tried to use error mitigation to check whether barren plateaus can be removed. So the fourth one is applying error mitigation, but there is one paper which seems to suggest that error mitigation cannot help avoid barren plateau. So that is one point. And the last point here is, there was a recent paper. I won't say I have studied it too closely to give my own impression on it, and I haven't seen community's impression on this. But there was one paper not very long ago, this year, a few months ago, which kind of suggested that if you can come up with a technique which can avoid barren plateau in these variational algorithms, then you can actually simulate that algorithm using a classical machine also. So what it means is that if the calculation and everything that they showed is perfectly correct, there is nothing, no strong assumption or nothing there. What it means is that barren plateau is an unavoidable limitation of these variational algorithms. If you can come up with a technique for a particular problem where you can avoid barren plateau and therefore reach a very good convergence, it also implies that you could have done that on a classical computer itself. You don't need, so it's a problem which is easy to solve classically. You don't need a hybrid quantum classical algorithm for this. All of these things taken together kind of, I know, dilutes the interest in variational algorithms. But again, at the same time, as I said, variational algorithms give some very powerful scientific knowledge that we have today, and it's good to understand the limitations before going to some other directions. These are easy algorithms, these are very easy to implement algorithms, easy to understand algorithms, very good starting point. So okay, maybe I'll once more stop if there are questions. If not, I'll very quickly move towards QAOA. Okay, maybe let's do one thing. Maybe let me just go to QAOA first, and then if you have questions, we can also take that later on. Let's just go to QAOA and be careful about the time also. I hope this is visible. Yes. So what we didn't talk about all this time is, sorry, start from here. What we didn't talk about all this time is how do you create an ansatz? How do you take a problem of interest and not just start with some toy Hamiltonian? How do you take a problem of interest and build an ansatz from there? And as I said, QAOA is a variational algorithm. Therefore, everything that we discussed about variational algorithm holds for QAOA. So what we will particularly discuss is this this part. We know that if we want to solve a problem, any problem on a quantum computer, we can divide it into what we call as the Qiskit pattern. First, we need to map the problem to quantum circuits and operators. Next, we optimize the circuit for target hardware. Finally, we execute on the hardware. And finally, we post-process. What we will focus on is this mapping of problem to quantum circuits and operators. And we will see how we take a combinatorial optimization problem and we create the variational ansatz from that. So, okay, let's not go into what combinatorial optimization is too much. It's essentially something which you have a cost function and you want to either maximize or minimize that cost function based on some values. One very famous example is this knapsack problem. Say you are in a room and you want to steal some items from that room and you are carrying a bag, so your bag has some limited capacity, you cannot take everything from the room, you can only fill up the bag to its capacity. So we need to be careful that I want to steal those items which are more valuable. So if I have, say, a laptop and if I have a pencil sitting next to each other, I would rather take the laptop and not take the pencil. So this knapsack problem is a very classic example where you want to select the items, decide whether this item goes into the bag or it doesn't go into the bag, and you want to maximize the value of the item that you are selecting. And similarly, we can have many of these problems. Combinatorial optimization problems are known to be notoriously hard to solve. Exactly. Many of these problems are NP hard, and therefore we often settle for approximate solutions. Here, we will talk about this very famous problem called the max cut problem. What is this max cut problem? Let's assume that you have a graph here and I have given you two colors. You can color the nodes using only green or yellow, nothing else. You can put any way you want, but I would say that an edge UV is cut if the color of the two vertices are different. So example 0, 1. This edge is cut because one of them is green, one of them is yellow. I don't care about the order. You can always say that I will put green here and yellow here. The edge is still cut. That's fine. And here I would say that 1 and 3 is not cut because both of them are yellow. Once more, it doesn't matter which color you give. Only cut or not cut. This is what I am interested in. Now, this is some problem. This problem is, say, very interesting in telecommunication, because we all are using some signal, some service provider. And let's say I use Vodafone. So let's say that my phone is connecting to some tower nearby where I'm sitting. If that tower fails, will my phone stop working? Will I lose all my signal? No, it will connect to some other nearby tower. What if this second tower fails? It will connect to a third nearby tower. What if this third tower fails? Now the point is, see why a telecommunication service provider can be interested in this problem. Say there are 10 towers from which my phone can extract signals. One tower can fail, two towers can fail. The probability that all 10 of them fail at the same time is very low, unless something catastrophic happens, right? So this is the cut, that is like a tower is one color and I as the user is another color. And I want to see how many cuts you want, what is the maximum cut, how can you maximize the number of cuts so that the probability that all of them fails is very, very low, and therefore I'll have a very high customer satisfaction. Just a use case of this. Now, this problem is NP hard. This problem is something called APX hard, which means NP hard, I would say again in a very crude way, if there are like theoretical computer scientists or mathematicians here, please forgive me for saying it like this. So if it is an NP hard problem, loosely speaking, we don't have polynomial time algorithms to solve it. That doesn't say that we cannot have polynomial algorithms to solve it approximately. But APX hard means that there is a certain approximation ratio. If you can have a polynomial time algorithm which can give you a better approximation ratio than that limit, then also P is equal to NP. So what it means, you can neither solve this problem perfectly in polynomial time, nor can you solve this problem approximately to an arbitrary level of approximation in polynomial time. So this is a notoriously hard problem, and these are the kind of problems we would want to tackle on a quantum computer. Okay, so if we understand this problem, the first thing to do is to write the problem down into something called a QBO. QBO, quadratic unconstrained binary optimization. So this is the QBO format. Let's just check for one thing. We say that if the color is green, it is 1, 0, otherwise it's just binary assignment, right? You understand this. So let's take this 0, 1. So this is 1, this is 0, this is 1 times 0, 0. So since this edge is cut, I am getting a 1 here. Now, if I look into this edge, which is not cut, so this is 0 essentially, yellow is 0. So all of these terms are 0 and I am getting a 0. You can ask, what if both of them are green? Then also the edge is not cut. True. If they are green, then this is 1, this is 1. So 1 plus 1 is 2, minus 2, which is 0. So you see the way this is actually formulated, if you look into an edge UV, if the edge is cut, then the value of this will be 1. If it is not cut, then the value of this will be 0. So when you sum over all the edges, what this summation is telling you is how many edges are cut, right? As simple as that. You get 1 for every cut edge, you get 0 for every non-cut edge, and when you sum it over all the edges, it just counts how many edges are cut. And what we want to do is we want to find an assignment X. Like here I have just given green, yellow, something. Maybe there is some other assignment which is better than this. So I want to find some assignment X for which this summation is maximized. This is what my problem is. Like whatever we discussed here, mathematically speaking, this is what my problem representation is. And this is a cubo, so it is quadratic. First, let's see why this is quadratic. The highest degree is 2. This is degree 1, degree 1. This is a multiplication of 2 degree 1, so this is degree 2. It is cubo means you cannot have degree 3, degree 4 kind of terms. It's quadratic. It is unconstrained. Okay, let's come to D. It is binary. Each of them are zeros and ones. It is binary. It is optimization, we understand. Why is this unconstrained? So here I am saying that you maximize this cost function. Subject to, there is no subject to. What does it mean? Say you put everything as yellow. Is it a wrong solution? No. If you think clearly, it is not a wrong solution. Is it a bad solution? Yes, it's a very bad solution because none of the edges are cut. So your cut size is 0. If you put yellow on each of the vertex, or if you put green on each of the vertex, the solution is very bad. None of the edges are cut. But the solution is not wrong. There is nothing called a wrong solution here. There is only a quality of goodness. Your solution is good, your solution is better, your solution is best, your solution can never be wrong. That is what it means by unconstrained. There is no subject to, there is no constraint that you have to satisfy. So if time permits, we will see one constraint optimization later. So this is QBO. The max cut problem here, the first thing we need to do when we want to go to a quantum computer doesn't understand 0, 1. It understands +1, -1. Why? Because the eigenvalues and the eigenvectors, the eigenvalues of these Pauli matrices, any observable, any Hamiltonian that we were talking about can be built using the Pauli operators. The eigenvalues of the Pauli operators are +1, -1. So we can get eigenvalues from a quantum computer. A quantum computer therefore doesn't understand 0, 1. It understands +1, -1. So it is very easy to convert from 0, 1 to +1, -1. If we just take this conversation, see, x is a 0, 1 variable and z is a +1, -1 variable. When z is +1, x is 0, 1 -1, x is 0. When z is -1, this is 1 plus 1, 2 divided by 2, 1. So 1 is mapped to 0, -1 is mapped to 1. So this is a direct one-to-one conversion. So this is something very easy. And if you just try it out, I would really encourage you to go and try this out. That this was the QBO that we saw. If you just replace each of these terms, so this will be replaced by, this is, okay, when I say 1, this is essentially, yeah, let's call it 1 for now. Okay, let's stick to 1. So if you just put 1 minus ZU by 2, 1 minus ZV by 2 like this and simplify, it will turn out to be like this. So this is called the Hamiltonian. This is going from 0, 1 to +1, -1. Great. So now previously I was telling you that find an assignment of x such that this is maximized and x is between 0, 1. Now I will tell you the same thing, that find an assignment of z which can be +1 or -1 which maximizes this, right? Now see, what has this got to do with a quantum computer? I said that quantum computers understand +1, -1 because those are the eigenvalues of the Pauli operators. But these are just going from x to z. There is no Pauli operator involved here. So I need to convert this into operators. When I go to operator, usually it is denoted by this capital. These were small, this is denoted by capital. We will consider the z gate. If you remember, z acting on 0 is 0, z acting on 1 is -1. So this gives a +1 eigenvalue, this gives a -1 eigenvalue. So now I have something called a Hamiltonian. This is the Hamiltonian here, where Cz is half of, now 1 should become identity. Each of this term now becomes, instead of this term which can be +1, -1, we have an operator whose eigenvalues can be +1 or -1, right? So this is the Hamiltonian that we have been talking about. And as you see how it comes from the graph that we had, this is the Hamiltonian part, and UV, ZU, ZV, this comes from the edges which are there in the graph. Now my objective here is to maximize this Hamiltonian. That means I want to find the largest eigenvalue of Cz. But we already discussed that there are many well-known sophisticated algorithms like gradient descent, like APSCHE, which are classical algorithms, which are very good in finding the minimum. So it kind of, if you want to find the minimum of that, it is very good in finding the minimum. So if you look into this, half is a constant, identity is constant. This is the only variable, right? This ZU, ZV, this is the only variable. So instead of saying that you maximize this entire term, it is same as saying that you minimize ZU, ZV, correct? If you minimize ZU, ZV, then this entire term is maximized. How much you are subtracting from this, if that is reduced, then this gets maximized. So this problem, this Hamiltonian, is a maximization problem. Of course, it's a max cut problem. It's a maximization problem. I can equivalently write this, that instead of finding the largest eigenvalue of this, you want to find the minimum eigenvalue of this. Now we are back to what we just discussed previously, right? We have our Hamiltonian. That doesn't tell me how to create the ansatz. We have our Hamiltonian. Previously, we said that, okay, my Hamiltonian, let's start with an Ry gate, Ry theta. But here we can actually go and build a better circuit also, a better ansatz also. So I hope whatever we discussed till now give you an idea of how to build a Hamiltonian from a real world problem and not just take a toy problem and a toy Hamiltonian. The ansatz come from something called the adiabatic algorithm. So what is the adiabatic algorithm? I have my desired Hamiltonian. So instead of this Cz, just let's call it H, because H we were talking of Hamiltonian, but it's exactly the same thing. HP turns is for problem Hamiltonian, the problem that I want to solve. That is what I'm calling as HP. And I want to find the ground state of HP, right? But it is difficult to find the ground state of HP. That's what we have been talking about, because this is a very large Hamiltonian. It's difficult to calculate using classical systems. What can we do is how we approach a problem. Say I am trying to solve some maths problem and I'm finding it very difficult. So the teachers, you all will go and tell the students that, okay, start with some easy exercise of this same chapter, and you practice on that easy exercise, and as you get more comfortable you will be able to solve more and more difficult problems. That is precisely what we will do here. We will start with some Hamiltonian whose ground state is easy to find, and we call this the mixer Hamiltonian, HM. We call this the mixer Hamiltonian. There is no restriction on how you get HM. Okay, the only criteria is HM and HP cannot commute with each other. This is the only criteria. There is no other criteria on HM. Select as a however you want, but you want to make sure that the Hamiltonian is such that the ground state is easy to find. So just remembering this criteria, select your HM. Now I would prepare the system in the ground state of HM. This I can do because I have already selected HM to be a Hamiltonian whose ground state is easy to find. Next, I will evolve my Hamiltonian like this. So S goes from 0 to 1. If you see, when S is equal to 0, this part is not there. So I'm starting with HM. When S is equal to 1, this part vanishes. I am finishing in HP. So it is essentially going from HM to HP. That's what we said, right? So we will evolve the Hamiltonian such that it slowly it starts from HM, it slowly evolves and settles down in HP. And this adiabatic algorithm says that if you can do this evolution slow enough, and you start with the ground state of HM, it will settle down in the ground state of HP. Now the question is, what does slow enough means? Slow enough, let's not go into the mathematical detail of this at this point, but usually what is seen is that slow enough for most of the problems are means that your time should be at least exponentially large in the number of qubits. So we are back to the same game, right? You can think that, oh, you made all these things, you said so many mathematics and everything, you are back to the same game. We started by saying that you need exponential time to solve max cut. And here, after doing all of these things, you are saying that your adiabatic algorithm says that your evolution should be slow enough, which is it is exponential in the number of qubits to get this solution. But remember, for these kind of notoriously hard problems, we are often very happy to select approximate solutions. So what approximate solutions will do, instead of giving an infinite time or an exponentially large time to evolve from HM to HP, so instead of making this evolution like super slow, impractically slow, I can just make it a practical evolution, not too fast, not like just going from here to here, like very, very fast, but not also impractically slow. But the moment I don't don't actually conform to this requirement that it needs to be exponentially slow, what happens is I cannot guarantee that I will settle down in the ground state of HP. But hopefully we will settle down close to the ground state of HP. Not exactly in the ground state of HP, but close to the ground state of HP. So instead of saying that I would go like this and settle here, maybe if I just move a bit fast, I will just move off the trajectory a bit and I will settle down here. So that's an approximate solution. And for most of these problems, we are often very happy with approximate solutions. Great. Now, the question that can come to your mind and that should come to your mind is that all the quantum algorithms that okay, just one small thing is that this is kind of what annealing is about. That this is adiabatic algorithm, but not impractically slow. It's a practical timed adiabatic algorithm in some sense, if you think. Now, the other question that should be coming to your mind is that when we learned about quantum computing, there were some qubits, there were some gates, and you were measuring. This is also what you showed, what I showed you all when we were taking that RY gate, that you were starting with 0, you were applying the RY, and then you were measuring. Where is the qubit? Where is the gate? Where is the measurement? You just said that you take a Hamiltonian, you evolve the Hamiltonian. So where is the qubit? Where is the gate? Where is the measurement? There isn't. If we talk of adiabatic algorithm, there isn't. But QAOA is what is called the trotterization of QAA. So easier to think, before going to mathematics or anything. Just like when I am talking right now, it's an analog signal. But in my system, there is a analog to digital converter. What it does, it samples my analog signal in many locations and it creates some discrete version of it. The discrete version is transmitted through the network and it goes to your end, and then that discrete version is again converted into the analog signal, and it seems like you can listen to exactly what I am saying. You are as if listening to an analog signal. Now, if we do that discretization, when we sample the system, if we do the discretization, if we sample it very often, then higher the sampling, better is the solution, right? I mean, better is the discretization. The more we sample, the more accurately we can represent the analog signal with the digital signal. And strictly speaking, if we can sample at every point, theoretically speaking, if we can sample at every point, then we exactly recreate the analog signal, right? So here also you can think as if this is Here also you can think as if this is like a analog signal, it's a continuous motion. So what we will do is we will evolve this system using two unitaries. And these unitaries are kind of discretization of this continuous system. So here I have this UHP gamma, which is e to the power minus I gamma HP UHM beta, which is e to the power minus I beta HM. You can think of gamma and beta as the length of these lines, or equivalently the time of evolution. So I have taken this continuous step and I have divided it into two discrete unitary operators. These are my quantum gates. Now the next question obviously is, how do we know gamma and beta? We don't. So here comes the variational algorithm part. We don't know the actual values of gamma and beta. You can always say that, okay, you have carefully drawn this and made it seem like it is settling down pretty close here. But how do I know that this should have been the length? What if I had selected this up to here? Then I would have been way away, way off, right? So this is this is where the variational approach comes. You start with a trial wave function with some random values of gamma and beta, and we vary the values of gamma and beta till some convergence criteria. And we expect that if you can get good values of gamma and beta using some of the algorithms that we discussed, Kobila, SPSA, gradient descent, whichever you like more, we can get better and better solution. That means higher and higher values for max cut. Now, as I kind of started off by saying that this is like analog to digital sampling. So nobody said that you can only sample it once. In fact, if you sample it once, it is a very bad approximation. If you can sample it, strictly speaking, theoretically speaking, if you can sample it at every point, which means, okay, this is what is called P. I take this U HP gamma, UHM beta. These two taken together, one applying these two gets once is called P equal to once. Applying these two gets twice is called P equal to 2. Ideally, if you can take P equal to infinity, then you exactly trace out the continuous evolution and you are guaranteed to go and settle down in the ground state of HP. But you can understand that one guarantee is that the higher the value of P, you cannot get a worse solution by increasing the value of P. This I am telling in the absence of noise. In the presence of noise, things can change. In the absence of noise, for the ideal case of the algorithm, higher the value of P, expected your solution will be better or at least as good as your previous scenario, previous value of P. But remember, higher the value of P, more is the number of unknowns. So here you have one gamma and one beta whose best values you don't know. Here you have two gamma, two beta whose best values you don't know. So it is essentially saying that more the value of P, more is the number of unknown parameters, but it is not very bad also. It is only two parameters per P, right? So it is not very bad also. The QAOA algorithm will go like this, and it's the exact algorithm you will recognize that we have seen. We start with some random parameters for, say, some particular P. There will be P many gammas and P many betas. So here, this is gamma, this is beta. If P equal to 2, there are 2 gamma, 2 beta. So I will start with P values of gamma, P values of beta. Now I will prepare the initial state in the ground state of HM, which is my easy to prepare Hamiltonian. Now I will create a quantum state, which is this UHP gamma UHM beta applied again and again P times on the ground state. Finally, we calculate the expectation value, which gives me the expected size of the cut. And we ask one of those algorithms that we discussed that give me a new set of parameters, and I will try out from step 2 to step 5 again with this new set of parameters. It keeps on repeating again and again. We have understood this previously also. The main point here is how this is created. This was the emphasis of QAOA. How is this part created? How do you create the answers? So just for the sake of time, let me skip the constraint optimization. But just to tell you that although I said it's a quadratic unconstrained binary optimization, you can still use constraint optimization by taking the constraint as a penalty into the cost function and turning a constraint optimization problem into an unconstrained optimization problem. But how we create the quantum circuit from here, theoretically, we have understood. Practically, let us take Hm equal to sum over xi. If you remember, our HP was sum over ZU ZV, right? For each edge UV, it was sum over ZU ZV. And the only requirement of my HM was it should not commute with my HP. And X and Z anti-commute. So I am taking sum over Xi, that means Xi on each qubit. So it is going to anti-commute with the HP operator. Now ground state of Xi. Xi is the Pauli X matrix. If you don't remember this, just go ahead and calculate this once more. I'm sure you all have studied this, that the ground state of X is this plus state, 0 plus 1 over root 2. We know that a quantum computer always starts with this state 0. How do you go from 0 to plus? You apply a Hadamard gate. Where? On each qubit I. So here is my graph where I have this 4 qubits, 4 vertices. Each vertex corresponds to a qubit. So I will start by preparing 4 qubits and a Hadamard gate on each of the qubits. This is how I prepare the ground state of HM, right? Next we come to the problem Hamiltonian HP. This was my HP. For each edge, I was applying a ZZ operator on both. Now, this looks complicated, but it's not. If you see, just follow on with me for a moment. This is my operator, UHP gamma. What is UHP gamma? It is exponential of minus I gamma HP. What is HP? HP is sum over ZU ZV. So it is exponential of minus I gamma sum over ZU ZV. Now, if there is a summation in the exponent, I can take it down as the product of the individual terms, right? E to the power, say, a plus b is e to the power a times e to the power b. For those who are more mathematical, this is true when a and b commute, and these are all z terms, so they all commute with each other. So e to the power a plus b is e to the power a into e to the power b. That's what we took. We took the summation from the exponent and we take it down as the product of each of the individual terms. This operator, this exponential of minus I gamma ZU ZV, is called an RZZ operator. This is just called an RZZ operator. So I will apply RZZ operator where? For every edge. So I have an edge between 0 and 1. There will be an RZZ operator between 0 and 1. I have an edge between 1 and 2. There is an RZZ operator between 1 and 2. Then I have 2 and 3 between 2 and 3. So whenever there is an edge, there is an RZZ operator. The last thing is UHM beta. We have already seen HM, we have chosen at sum over xi here. So UHM beta, same calculation, UHM beta exponentiation of minus I beta HM, and HM is sum over xi. This is sum over xi, and there is summation in the exponent. I can take it down as the product of the individual terms, and here I get this pi I Rx beta. This is the Rx gate. This exponentiation of minus I beta xi is the Rx operator. Where am I applying this Rx operator? On every qubit. So finally, this is my entire quantum circuit. This is my entire ansatz. Here, as you see, we started with this H, which is creating the initial state. This is my UHP gamma. And if you see here, we only have gamma as the placeholder because I don't know the best parameter values that I will have to find out by running this algorithm. And finally, we have, I don't know why this is not showing up. This should be Rx beta on each qubit. So this part, this ZZ operator and Rx operator is this part. So if you want to repeat this as p equal to 2, this part will be repeated twice, not the Hadamard part. You only prepare the ground state once. Then if you want P equal to 2, you repeat this again. Just place the same thing again after this. P equal to 3, repeat this 3 times, and so on. And finally, you measure. So that's how you create a quantum circuit, the ansatz for a system. This we saw for in terms of a mm, this we saw in terms of a combinatorial optimization problem, and we have already seen the other steps before. And yeah, that's more or less what I wanted to cover. I would just say one small thing very quickly. I know we are out of time. Just one small thing. If you guys are interested in this, please look into. I hope this screen is visible. So just look into this Qiskit add-on optimization mapper. The theory that I discussed is already here, but if you look into this Qiskit add-on optimization mapper, this gives you a very nice way by which, so what we did, we took a problem, we had a problem, we converted it into a QBO. From QBO, we had the Hamiltonian, and from the Hamiltonian, we created the QAOA circuit. All of that you can do using only 3 to 4 lines of codes using this Qiskit add-on optimization mapper. And for important problems, which are very well studied problems, you have these applications, say all these you see bin packing, click exact cover, graph partition, independent set, knapsack, max cut that we discussed. So many of these problems, TSP, vehicle routing, vertex cover, you already have the problem defined. All you need to give is the graph as the input, and in 3 lines, it will create you the QAOS circuit. If you have some other problem that you are interested to, this package also allows you to write your own problem. Say you have an ILP, you have a normal linear program, you can input any of those problems here and then use them to convert to QBO from your say ILP to QBO, from QBO down to your Hamiltonian. All of these are doable very easily using this new Qiskit add-on. It was kind of uh, it's now around a month old since it was made public. So yeah, I'll stop here. Thanks a lot for. Yeah, there is one question. Is it related to max flow minimal cut? No, what we discussed was the max cut problem, the max flow mean cut. It is more related to the mean cut problem. Mean cut is a classically easy problem. Here we are kind of talking about more classically hard problems. Yeah, let me share the GitHub link, and I can also share this with you. Hopefully this will be helpful. Yeah, I'm also sharing this particular notebook with you. This is a tutorial that I created for a recent um, conference, the Supercomputing India, on how you use the quantum optimization mapper. Here I have shown both how you take, I've just taken an example of a warehouse storage allocation problem, which is not a problem which is part of that application um, things that I showed you. And how do you take a problem like that, create a linear program from there where the variables can be binary, where the variables can be integers, there are constraints, all of those, and how you very easily convert it into a QAOA. And I have also shown how you take one of the application problems like the maximum uh, independent set problem, and it's even easier to convert that into a QAOA. So hopefully this will also be useful for your case. So yeah, I'll stop here. Thanks a lot for sticking on for so late.
Thank you so much, sir, for this insightful session, and thanks to all the participants to join this session. Yeah, so we will meet tomorrow at 3 o'clock. So once again, thank you all, and thank you, Ritaji sir, for this session. Thank you so much.
Thank you. Thank you.